Hi, this is Stephen Barrett from Martin Valley Community College. This is for CSIT 256, Computer Architecture and Assembly Language. And this is meant to be the overview for Stallings Chapter 14. On one topic, I may dive into a little more depth than I normally would in an overview, but I have a feeling this is going to be the only video for Stallings Chapter 14. Some of the topics at the beginning of the chapter are going to look very much familiar as being the same as some prior topics or topics from some prior chapters. And some of it is meant to be a review for things that will be looked over within the chapter. And what I'll try to address is the delta, sort of the new stuff, or at least some of the new things. Registers. Now, we've been talking about registers all along, but what I like in the book for Chapter 14 does get into user visible registers versus control and status registers. The user visible registers are the ones that we can see, meaning we can access what's there. The control and status registers are the ones that when we're programming, we can't. Well, there's a little footnote to that. It's meant to be for the processor for control and status registers, but there are some privileged instructions within the operating system that can access those. So the operating system does have some privileges that we programmers do not. And there could be situations where they're being looked or evaluated, or there's a command based on something in there. But in terms of us programming and assembly, we're not going to see those registers. Now, something that was introduced in Chapter 2 was the idea of pipelining. And the example I did back then, actually, let's jump back. The example I did back then, I only showed 4 stages. I said we were going to look at different stages in the instruction cycle later, which ended up being Chapter 3. And I showed that without pipelining is that at any one point in time, an instruction is either being fetched or decoded or executed or stored. And after it completely finishes one instruction, it then goes and gets the next instruction, fetches it, decodes it, executes it, and potentially stores the results. And so again, back in Chapter 2, one of the things we meant in pipelining is we would have additional units on the processor that would handle, the prefetch unit would handle the fetching, the decode unit would handle the decoding, the bus interface unit would handle, it actually does both getting data, but also writing data back to memory. And so then with pipelining, after instruction 1 is fetched, then at the next unit of time, instruction 1 can be decoded as instruction 2 is fetched. And the next unit of time, instruction 1 is decoded, instruction 1 is executed as 2 is decoded as 3 is fetched. Well, we saw that previously. I mean, this Groundhog Day, I'm making us do Groundhog Day because I'm having us relive that. A little hiccup there because I got a hiccup again. I'm sorry. So what I'll be looking at in Chapter 14 in terms of the pipelining is we'll look at 6 of the stages as opposed to the 4 I did previously. So fetch of the instruction, decode of the instruction, calculate the operands, fetch the operands, execute the instruction, and then write operands, write them back to memory. Now, this table is laid out differently than the one that we saw in Chapter 2, in that the instructions are listed here. Time is showed advancing, and then we're seeing the 6 stages for each one. So at time 0, instruction 1 is being fetched. At time 1, instruction 1 is being decoded as instruction 2 is fetched. At time 2, instruction 1, we're calculating the operands as instruction 2 is being decoded as instruction 3 is being fetched. Now, what I highlighted in red is when the execution is taking place. So if we're starting a sensor application, let's say we're beginning on instruction 1, there's a delay in time before the first actual instruction is being carried out. But the next unit of time, the next instruction is being carried out. The next unit of time, the next instruction is being carried out. So that we don't have to wait between time for doing the execution of an instruction. Well, one of the things that we'll see in the chapter is talking about a branch penalty. So imagine if when instruction 3 is being executed, suppose that actually is a conditional jump. And it says, okay, if this condition is true, jump to instruction 15. Well, instruction 15 isn't in the pipeline. And also what that would mean is the instructions that we started in the pipeline, we don't need those anymore. And so if it has to now jump to instruction 15 has to be fetched, and then it has to be decoded, and then the operands have to be calculated, and then the operands have to be fetched, and then finally it will start executing that instruction 15. And so what we end up with, referred to as a branch penalty, is time lost where no execution is being done because it's then grabbing that next set of instructions. So a couple ways to address this that's pointed out in the chapter. One is pre-fetch branch target. So imagine if when instruction 3 is being decoded, it suddenly realized, hey, wait a minute, this is a branch. We may have to branch somewhere else. Well, where are we going to branch to? Instruction 15. Okay, let's fetch it at the same time. So at the next unit of time, it's proceeding with instruction 3 in terms of its now calculated operands, but it's now basically loading the pipeline with what instruction 15 is, just in case we branch in that direction. So by the time we get to this point in time, when this is being executed, at the next unit of time, we either will execute instruction 4 or we'll execute instruction 15, and we won't have a loss of time as we go from basically executing instruction 3 to then executing instruction 4 or 15. And the book mentions one of the computers or one of the processors that takes advantage of that, and we'll go into a little more detail on it. But what that does is that is one way to address the branch penalty. Something that's mentioned, I'm not going to have a fancy picture for it, and I'm not going to do a good job about it, and I'll just say that another thing that the chapter will look at is the idea of branch prediction. And it'll look at 3 ways in terms of static, meaning not based on history, where it can predict where we go. And then the other one, dynamic, is based on history, which if a program has been run a number of times, or if it's a section of a program that's been run before, it actually, in a sense, can build its own statistics and then figure out where to branch or what to bring into the pipeline, thinking it's going to branch in that direction. The latter part of chapter 14 gets into ARM, the ARM architecture, which had a couple names over time because initially, well, anyway, has a couple of names over time, but the R in ARM, reduced instruction set computing. So what happened over time with like the processors that we're using is the instruction set became more complex. And so like in chapter 9 of Irvine, we saw support that was put in there for arrays. Well, that complicated the processor by putting in the support for arrays. And the idea was, well, if we, using the computers at the speed we have now, deal with a smaller instruction set, we can execute more instructions per second. And so the idea of the RISC, reduced instruction set, there's fewer instructions to deal with. And the other thing is there was a recognition that not every application would lend itself to it, but there would be a number of applications that would. And so besides the instruction set being reduced, there are some, and the chapter gets into more than what I've listed here. But a key thing, which is unusual, is that all the operands have to be in registers. So you know how we're able to do like add, EAX, comma, money lost, and so we can refer to the memory money lost. Imagine if we can only do add, EAX, comma, EBX. And so we'd have to load the money lost in EBX and then add it to EAX. So kind of a big thing in terms of but in terms of reduced, it reduces the complexity of the processor, because then it's just dealing, when it comes to add, it's only dealing with registers. It doesn't have to then fetch the operand. It's up to us to write the code to fetch the operand. The other thing that's mentioned in terms of ARM is addresses processor modes. User mode would be what we program in, and then there are privileged modes, which would be based on certain conditions, or operating system will be carrying things out, or handling interrupts, and which exception handling is something that is mentioned in the chapter as well. They give a list of where ARM is used, such as things like smartphones, but in general, or I shouldn't say in general, but one of the things it's used a number of times for are embedded systems. They require less electricity, can actually run on a battery as opposed to being plugged in. And the fact that they can run on a battery, it's easier to embed them in yet even smaller systems. Okay, that was a long overview, but that's Stallings chapter 14. We got a train wreck. Oh, I should edit that out.